Okay, so today let's look at section 12.4. The topic is concavity. Okay, and concavity talks about how the graph of a given function bends or turns. Okay, or turns. And so let's take a look at this graph first. Okay, and then we'll talk about the definition here. See, this is a function, and you can see, guys, right now I'm gonna do one thing. I'm gonna draw a couple of tangent lines across this curve, okay? And I would like to see is there some patterns I can find. Okay, so if I put it here, right? And then some tangent lines here, right? And then there will be a position which becomes into flat, right? Which you can see from the previous part. We know that at this point is a critical point. Okay. And then I can draw, this, and I can even draw something here. Okay. And if you continue, guys, do you agree that starting from some places here, when I draw the tangent line, this is not a critical point, right? Okay. So this is what we just draw. Okay. I hope you can see it clearly. And let's look at, is there some patterns or some features we can tell? First of all, guys, do you agree that on the first half part, when we draw the tangent lines, and then those tangent lines is above the curve, right? In other words, it's on top of the curve. And there after some points, I labeled a point here, okay? And you can see that those tangent lines, it becomes below the curves, right? So that's one thing we can observe. Okay, so that's the first thing. The second thing you can think of, let's think of in this way. Before my slope of the tangent line for here, it is positive, right? And then it's still positive, but it becomes smaller. And then it becomes into 0. And then starting from here, become more and more steep, but in a negative way. So in other words, it become more and more smaller. Okay, become more and more smaller. Right? So let's label it here. So in this part, the first derivative is positive. In this piece, first derivative becomes 0. In this piece, first derivative is less than 0. Okay, less than 0. And then now let's look at what about the trend of our first derivative changes. You see from here, I have a very small negative slope, right? And then still negative. So for this part, you see that the derivative actually is less than 0. Up to this point, the derivative becomes 0. And then starting from here, after crossing this part, do you agree that our slope is greater than 0, right? So this is what we can take. And also, you see, guys, this derivative before it was starting from here is positive, 0, and negative. Do you agree that actually as a function, the derivative function, it's decreasing, right? So you start from a positive number, it becomes into 0, and then it continue to become a negative number. So do you agree that the monotonic property for the derivative function for this part is decreasing, right? Okay. And then let's look at it here. So the derivative part is negative, it becomes 0, and then it becomes positive. So do you see that the derivative function from here to here to here, actually it increases, right? So that's what we can think about it, based on the previous section we already learned, okay? And we do have a name for those two different behaviors, which is called the concavity, okay? Concavity. And more specifically, we're gonna put them into 2 categories, okay? And this is our summary. So if we have a graph of a differentiable function y equals fx, and we call the graph of the function is concave up if the derivative function is increasing on the interval I. Okay, for example, we can look at this part, right? So if we look at this, you will see that the derivative function from some places here up to here, it's increasing because it's from a negative to 0 to positive. So it's keep climbing, okay. And the other case is if the derivative function is decreasing on one interval I, and we have name is called concave down. And concave down, you can see that it's exactly this situation, right? So you have positive number, it becomes 0, it becomes negative. So the derivative function actually is decreasing, okay? So also, guys, when we talk about the concavities here, sometimes I like to use this hand shape, like if it's concave up, right, like this way, and if it's concave down, like this way, okay? So, and also, guys, do you agree that from here, this is concave down? Let me label this part. So this is concave down, and then for here, this is concave up, right? So the concavity changes at some places, and for here I plotted a point, and we have a name for this point, which is the point of inflection, okay, point of inflection. And the definition of the point of inflection is where the concavity changes. It can be changes from concave down to concave up, or it changes from concave up to concave down. If you have a concave up and then concave up, then it's not a point of inflection, okay? And so this is about the basic ideas about the concavity. Also, guys, before we look at the other side, let me touch a little bit more about the graph with the local extrema. And you see that, guys, for here, we all know that this point is a critical point, right? And similar for this one. But meanwhile, we also know that this is a relative max. This part is a relative mean, right? This is a relative mean. And you can tell that when we have a critical point, and that critical point also lies in the concave down interval, that critical point will always be a relative maximum, okay? This is part of the theorem. It's called the second derivative test for the relative extrema. Okay. Similarly, if you have a critical point, meanwhile, that critical point lies in the interval which the graph of the function is concave up, then you're gonna have a local minimum. Okay, so put it all pieces together. Now let's look at the other side. Some definitions here. Okay. First of all, there's a new term. A function whose graph is concave up will also have a name. It's called as convex. Okay, and I believe that this is a term that you hear a lot. Okay, and some of you, if you know a little bit about linear programming, and you will see that if the problem is convex, and then it's easy to solve. But if it's not convex, it's very challenging to solve. Okay, so that's a part of the optimization courses. Okay, so I'll skip this part. Now, so let's look at the what we call the second derivative test for concavity. Okay, as we discussed, when we call it concave up, then we know that the derivative function is increasing, right? And we also know that, okay, if a function is increasing, then the derivative it's greater than 0. This is what we learned from 4.2 and 4.3, right? Couldn't remember exactly which section, but it's one of the section there. So, and this is the definition. If we have a function is twice differentiable, in other words, second derivatives exist on the given interval. If the second derivative is positive, okay, on this interval, then the function is concave up, right? Because if it's concave up, that means the derivative function is increasing. Then the derivative of the derivative function must be greater than 0, and which is here. Okay. Similarly, if second derivative is less than 0 on I, and then we call that the function is concave down. Okay, so if second derivative is less than 0, that is concave down. Okay, and also point of inflection is where the cavity changes. Okay, we talk about that. So this covers the broad picture in section 4.4, and later we're gonna start with one example. Okay.